Okay, let's just kind of get started. So this is like multivariable calculus. I'm taking this course, and so they have come up with some new definitions which I basically need to go through. It will just be like very simple sort of definitions, but still, let's just go through all of it. So yeah, it will take some time. Okay, let's just get started. You have a bit of some examples. So in one of the previous classes, they defined this thing called curvature. So let's say you have some curve. Actually, let's not even draw an axis. Just say you have some curve. You have some starting point from which you have the arc length defining this curve. So you have some S thing, or you could have some parameterized curve. So this could be like r of t, where r is a point in 2D. So basically rt is in real squared. Um, but you can similarly write this thing as something like r tilde s, where r tilde is some sort of a reparameterization. We call it a unit reparameterization. But in any case, the point is that r of t is a parameterization of this curve. The curvature is just defined as it's defined as the magnitude of d tau by ds. Sorry, d capital T by ds. Yeah, actually the tau thing is reserved for something else. Where capital T is this unit tangent vector. So it's just the unit tangent vector, which is basically like the velocity vector. So v of t upon its magnitude, right? So how this changes with respect to the arc length, that's what defines our kappa, which is the curvature. So you can rewrite this whole thing as you know, dt upon d small t, where t is the parameter, and then this upon ds upon dt. But remember, this thing is exactly just the speed, and which is like the magnitude of the velocity. So this just happens to be this. And now, yeah, this is the equation that usually you use. Sure. So that's the curvature that they've defined. Pretty simple, really. Okay, now they are going to something else. Unit speed curves. So basically the cases where your velocity vector has magnitude 1, right? They just define this basically. Okay, and then they are going to a new definition called the reparameterization. So what basically they're saying is like, this curve, you could represent it as r of t, or you could represent it as in some different way, like r tilde of t tilde. And they've given like an example. For example, circle can be represented as like cosine t sine t, but it can also be represented as sine t comma cosine t, right? And obviously these two parameters, the t value in both of these parameterizations, they are not the same. So to convert between these, you have this reparameterization map, which is denoted as phi. So basically what happens is, your r of t you rewrite this thing as r tilde of t tilde, where your t is given by phi of t tilde, right? Yeah. So essentially, the full equation would be something like r tilde t tilde is equal to r of phi t tilde, right? Yeah. So that's a reparameterization. Basically, like, if you you know, have some other form of the curve, I mean other parameterization of the curve, effectively it's the same, like no matter how you parameterize it, right? All of these would be parameterizable within each other. Yeah. Also there's like an extra condition for phi, that this should be a smooth bijective map, right? So what I mean is that the forward direction of phi, that is smooth, as in you can do the epsilon delta thing over there. I mean that's like yeah, differentiable basically. That phi is differentiable. At the same time, phi inverse is also differentiable, right? I should be saying differentiable. It shouldn't be that. I should just be saying it's continuous, but like, I guess differentiable is a better word to say over here, because they're saying it's smooth. So yeah. Uh, how do you define a smooth function? What is a smooth function? I don't know. I'm gonna search that. Right. It takes some time to open up. So just what is a smooth smooth function. Oh, okay. So it's that thing, like it's first order differentiable, second order differentiable, all that stuff. Right. So a function of class C infinity is an infinitely differentiable. That okay, fine. So it's a C infinity class, as in something like e power x, or e power j omega t or something like that, which is like infinitely differentiable. When we say infinitely differentiable, at one point the derivative could just be the zero function, and then at that point, like, you just get like zero all the way, but that would still be like a smooth function. So any polynomial, for example, is a smooth function. Yeah. So sure, we now know like what a parameterization or reparameterization is. So you need this phi, the reparameterization map, to be a smooth bijective function, and then you can convert this into r of t into r tilde of t tilde. Anyway, the reason we are doing all of this is because what we want to do is that for every single curve, we want to have a very specific kind of parameterization which has the velocity vector equal to 1 at all points. And I'm saying any kind of curve, but essentially your velocity should not be 0 at any point, no matter however you parameterize it, because so if in one parameterization your velocity is 0 at some point, that's a problem, right? That's kind of a problem, and so that should not happen, right? Yeah, okay. So let's just get to it, right? So like, for example, a curve like this is not a curve that you want to be reparameterizing because over here you can see that the velocity is 0, right? It goes over there and then it comes back. So the acceleration is something, but the velocity is 0 at that point. Anyway, what was I doing? Yeah, inverse map is not so sure. So these alpha tilde, beta tilde, these are, so this is an interval basically. Like, so what it's saying is that your t tilde, it belongs to this open interval alpha tilde, beta tilde. Similarly, like your t belongs to alpha, beta. So your parameterization map is going from your t tilde to t, which is basically from this domain to this codomain. Sure. Anyway, so the circle example is there. Then you also have regular, right? So a regular point is basically any point where your velocity is not 0, right? However, like parameterization you are doing. So when I say velocity, I mean like the derivative with respect to the parameter, right? So yeah, that's not 0. In that case, that point is a regular point. And if it is 0, it will never be a regular point. No matter how much you reparameterize, do whatever you want to, you will never have it. And it's pretty easy to see. I mean, you have this equation. Let's say you did reparameterize this thing, right? You parameterize your curve using r tilde t tilde, right? So at t equal to t naught, you were not getting a regular point. You were getting an irregular point. Then at the corresponding t tilde, which is like phi inverse of t naught, you should also be not able to get a regular point. That is, your velocity should be 0, and that's not so hard to prove. Okay, so let's do this thing. So you'll just have the velocity, which is like r tilde t tilde, the derivative of that is r dash of that, sure, at some t tilde value, which we'll put later on, but the derivative of this thing with respect to t tilde, that's what we're kind of going for. So it's just r dash phi t tilde, and then the inside stuff's derivative, which is just phi dash t tilde, right? Remember, this is actually a differentiable function. Now the thing is that this r dash of sorry, so phi t tilde, that would just be t naught. And so r dash of t naught, that, so I'm just gonna call this like t tilde naught. So basically like phi of t tilde naught, that thing is equal to t naught. So this quantity is just going to be 0 because it's the velocity vector. So it doesn't matter what this thing is, your r dash of t tilde naught is going to be 0, right? So the corresponding point also is not regular, right? So a point is regular only if it is regular in some other parameterization, right? But we can now extend that and say that, So it would be impossible for a point to be regular in one parameterization and non-regular in the other parameterization, right? Because if it was in the other parameterization irregular, it would also be irregular in the first parameterization. So either a point is regular or not, no matter however you parameterize the curve. Okay, that was awesome. Yeah. So next they define something called a regular curve, where all the points are are regular. Then they go for a unit speed reparameterization. So basically, you reparameterize r of t as r tilde of t tilde such that this r tilde dash t tilde thing, it has a unit magnitude at all times. And this is actually pretty easy to do because of the last equation we saw. So r tilde dash t tilde that is, so basically this is just r of phi of t tilde, right? So this would just be like r dash of phi t tilde, and then this guy's derivative is just like phi dash of t tilde, right? Yeah, cool. So what we want is that this guy's magnitude should be 1, which is to say that the magnitude of r dash, and then so this thing is just t, right? That and that times the magnitude of this quantity, which is just so I'm writing this, but it should just be an absolute value because, like, come on, it's a real number, right? So phi dash of this t tilde, I think you can also rewrite this as something like d small t upon d tilde dt tilde. Oh wow, that was very messed up, but in any case, so you can read it as 1 upon d t tilde upon dt, but guess what is that? That's just the derivative of phi inverse. So it's just 1 upon phi inverse's derivative at some t value, right? Right. So what that means is, what you want is just r dash of t, its magnitude should be equal to the absolute value of phi inverse dash t, right? Yeah. They're also writing this s stuff, which is crazy, but whatever. Right. Right. So the point was, how do you get to this? Yeah. So your velocity. So basically, your speed is given. What about the direction? The direction is actually. Oh, that's a weird thing, isn't it? Sure. What would be your direction? Well, I mean, it doesn't matter, right? Because, like, your parameterization, it like sets, so the direction will be the same in any case. Yeah, I mean, it's kind of obvious that you know, what was I going to say? I kind of forgot that. So once again, what we want is just like r tilde of t tilde. That's our objective, and so you know that this thing is just equal to r of phi of t tilde. So once you can figure out what phi of so once you can figure out these two things, r and phi of t, you would be done pretty much. Yeah, sure. So then how do we go around doing this? So the magnitude of this thing is 1 at all points, right? R of t tilde is just equal to this quantity, which means, so this is just the integral of r dash of, so I'm just taking a derivative like directly over there. In fact, so we just want to find r of t, right? Yeah, sure. So how do you find r of t? It's just the integration of r of tau. So I'm using tau. It's used for a different thing, but well, whatever. You just got d tau over there. and this is from tau equal to some 0 to something. Yeah, yeah, right, something, right? So 0 to hey, so the okay, no, the question is actually slightly different. The thing is, you have been given what r is. So you are given r of t, and you want to find a phi such that this stuff happens, right? So we are essentially just going to integrate this equation, and that will in fact give us what phi is, right? Yeah. Oh, so you can do a very nice thing over here. We can, right? So since we know that an irregular point remains irregular regardless of parameterization, right? So what that means is a unit reparameterization that cannot a unit parameterization cannot ever be reparameterized into something which is irregular at some point. But what that means is that the magnitude of r dash of t, or I should say r tilde, whatever. So this thing is never going to be equal to 0, right? Which means it can, so this, yeah, right. So this is never going to be equal to 0, which means that the absolute value of phi inverse dash of t, that is never going to be equal to 0. But that means that phi inverse dash of t, this function, it can never cross from positive to negative. So it's either always positive or always negative, right? Because if it were to cross, you can see that's going to be like crossing 0 at some point. So that doesn't make sense. So what that means is either your phi inverse dash of t is equal to just positive r dash of t magnitude, or negative. So I'm gonna keep the negative one aside and just deal with this. Okay, why did this happen? I hate this. Right, so I'm just gonna keep that aside for now, and it can certainly be negative, but whatever. So I'm just gonna integrate that. So what does this give us? It just gives us phi inverse of t is equal to the integration. So just pick a point where this thing is 0. Just call this thing as t naught, all the way till some t, whatever. So at t naught, your phi inverse of t naught is just 0. Sure. Yeah, that seems about right. And so you just got like r dash, the magnitude of that. So just the magnitude of, and I'm just gonna write it as velocity of vector right now, but whatever. So that is the parameterization that you want. I mean the reparameterization. So just plugging that in, you can get your r tilde. So r tilde of t tilde is just r of phi of t tilde, but now phi of t tilde, you get it by this thing. So yeah, you know the phi inverse thing now, right? Yep. Right. Hey, so this thing is actually very much familiar, isn't it? Yeah. Okay. So this is the arc length, in fact. So it's just s of t minus s of t0, isn't it? Yep. That's how it is. So then you know what phi inverse is, right? So what we can do is just rewrite this whole thing as r tilde of phi inverse of t is equal to r of t. So now you know what like r of t is. You can figure out what this thing is. That this shouldn't be a problematic thing at all. The point is, how do you get phi of t? That's a problem. So just phi inverse of t, that's easy. So just r tilde of s sub t, right, minus s sub t0, that's equal to r of t, right? Yeah, sure. Hey, so we can just redefine this whole thing, can't we? Sure we can. Oh, that's weird. So phi of t is like s of t minus something. So all you're saying is just add some constant. Wait, but t naught is a very specific thing. T naught is when your phi, but you can set your representation like that in any case, right? Yeah. Okay, cool. So far what we've got is this thing. Okay, so let's just see what they did. So what they are doing is that oh, they're doing the same thing. R tilde of s is equal to r of t, sure, but where did the st not go? Did you just set it to be 0 or something? I don't know. So oh, okay, they are saying that one of the ways to reparameterize is just this thing, which works. I mean, clearly it works. If it's r tilde of s, well, this guy's derivative is, sure, that actually does work, doesn't it? Mm-hmm. Yeah, okay, then the velocity would just be like the derivative of this thing. So just like d by ds of r tilde of s upon ds. Yes, right. But then, yeah, so upon ds, huh? Oh, but the magnitude is just that. So yeah, okay, that actually does work out. Yeah, that makes sense. Because the thing is that, so dr tilde of s upon ds, right? What is this thing? That is just like the, I mean, just a norm of this whole thing. That is the norm of dr tilde of s, right? Upon the absolute value of ds, which is like a positive constant. Just assume that, so a positive number. So then this just becomes something like on a small increment in your arc length. So like if you just travel a bit more distance, how much does your position vector change? Like the change in magnitude, basically. I shouldn't say the change in magnitude, but the magnitude of the change. And obviously the r vector thing is just this vector, so it's magnitude, which is obviously just ds, so just ds by ds. That's 1. So what that means is this reparameterization actually works. It's a unit reparameterization, but is it the only reparameterization? That's the question. And turns out that no, it's not. As we saw, you just need like phi inverse of t equal to integration like t naught to t this stuff, right? Which is just something like that. So basically phi inverse of t equal to s plus some sort of constant, that works. At the same time, we know that the negative thing also works, right? So just I'm gonna put a plus minus over there. So just plus minus the arc length plus some constant. That's the family of all of the reparameterization that would work. Yeah. So here this u is just phi inverse. Okay, cool. So that that covers this stuff, the unit reparameterization. But like, why do we care so much? We care because with this we can do a lot of nice things, because what it does is like it allows us to use the arc length to rewrite everything with unit speed everywhere, right? So then yeah, right. So then we can define a few more things. First, we define something called assigned curvature. So we know that curvature previously was defined as just dt over ds, right? So now you're just thinking of this t thing as like just the velocity itself at this point. So this would just be like r dash of s, sure, because everything is parameterized using s instead of t. So yeah, I mean r dash of s is just unit vector already. Cool. And then what? So you want the signed curvature. So this is an unsigned curvature, right? This does not really tell us like how the curve is actually moving, right? We want to know that as well. So the most sensible thing of doing it is just so how can curvature be? It can be either like this or like this, right? In both the cases it would still be the same value, like this kappa would still be the same value, but we want to have a sign so that we can determine is it upward or downward or whatever. So the way that we do it is you have some curve, you just take some unit vector, like I'm just taking the x-axis right now, and so whatever is your tangent vector, right? This is your tangent vector. This angle, right? Let's call this as phi. Actually, let's not call this as phi. What is it called here? It's psi basically. So let's call this as psi. So this psi, which is actually a function of the position, which is s, right? Yeah. This, like the tan of this angle is obviously the slope, right? Yeah. So what we want is just the derivative of this with respect to s. So your kappa, it just becomes like d psi by ds, the magnitude of that, obviously. Yeah, that's that's what your curvature is. Okay, don't actually put a magnitude because we want unsigned one, so we want a signed curvature, right? So yeah, that's how it's defined. Sure. Very unsatisfactory because we don't even know if these two curvatures are the same, and that's what they are actually the same. I mean, if you think about it, what is this thing? This thing is, so it's the magnitude of r dash s upon ds. So it's just, how does the unit tangent vector move, right? That thing's velocity and all that. So how do you like write the unit tangent vector? It's just this thing, right? Cosine of psi comma sine of psi. Sure. Now the derivative of that would be something like negative sine of psi, cosine of psi, and then d psi by ds. Alright. So yeah, with respect to s, this will be the derivative. Now I just want the magnitude of that. What is that? Okay, why did I write ds over there? I don't know. It's supposed to be dr. Yeah, I guess that makes sense. So what was I going to do exactly? Right, so this r dash of s was this thing, and so you take a derivative of that, you get this thing. The magnitude of that is just 1 because this is a 1, and that times the magnitude of this thing. So clearly d psi by ds, the magnitude of that is the same thing as this quantity, which means that in terms of magnitude these two are the same except this has a sign, and that's a nice thing. Okay, so we have defined sine curvature. And so you can write this as r double dot, which is like dt by ds, because remember t was now just the velocity itself because it's unit velocity everywhere. And since it's like a, how do I say this thing? Since it's a unit vector all the time, right? Since your t is a unit vector, what's going to happen is that this thing, your dt by ds, it's going to be in the direction perpendicular to t. You don't believe me? You can see this easily. The thing is that t square is just equal to 1 all the time. So what does that mean? That means like dt square is equal to 0, but that just means like so this thing is just t dot t, right? So t vector dot t vector, we just have t of that, and as goes with any sort of inner product or any bilinear product, in fact, what happens is we can just write this as this thing. And then since dot product is like commutative, we can write this as this thing, right? But then you can in fact rewrite this as this thing. Yep. Yeah, and this little bit is actually, you know what, let's not write it like that, never mind. So yeah, this happens, and so divided by ds, what do you get? Just get like d by ds of magnitude of t square, that's equal to 0, that's equal to 2 times this stuff. What does that mean? That means that dt upon ds, that's perpendicular to t. And what's dt upon ds? That is I mean, it's magnitude, it's kappa, isn't it? Right. Okay, that was some weird thing, but anyway, this dt upon ds thing is perpendicular to t. That's also called the normal vector now. I mean, it is a normal vector. Anything perpendicular to our tangent vector is the normal vector, but in this case the normal vector is just dt upon ds, which is a nice thing. So what we just have is like with a unitary parameterization, your t vector is just dr by ds, and your n vector is just d square r upon ds square. Cool, isn't it? Yeah, right. So I was going to say something, I just kind of forgot. Scalar is never mind. So this is like some cool definitions and that's it, but move on. So now we have this theorem which says that let kappa be the sign curvature, right, of a unit speed curve, right. Further, r tilde in any other unit speed curve. So okay, so what this thing is saying is that kappa completely determines what curve you are going to get, right. So whatever curve you have, you can boil it down to a unit reparameterization. So if your unit reparameterization has the sine curvature function kappa, in that case its shape is unique, as in you can rotate and translate it, but its shape will not like change apart from that, right. Yeah, that's what they're saying. Essentially what they're saying is like fix a kappa and the shape of your curve fixes up to translation and rotation, right. And that isn't hard to show. So what's kappa once again? Well, kappa is just d psi of d, so d psi by ds, right. Yeah, and so let's just say that initially you are starting off at some s equal to 0 point, right, and you have some sort of a velocity vector. How do I even show this stuff? Yeah, I mean, how do I even show this stuff? Actually, they have probably given me, yeah, they've given me a proof in fact already, but let's just try to prove it by ourselves. So we're given some original point as 0, and you're also knowing the velocity, which will be magnitude is just 1, and the angle it makes with, let's just arbitrarily choose the x-axis because it doesn't really matter what unit vector you have. So let's just say the x-axis, right. So this angle is psi. Cool. So what this gives us is something like the dr vector thing, that's just equal to your ds times cosine psi sine psi thing, right. Okay. So your psi is fixed when this happens. Okay, so you can rewrite this whole thing as ds e power I psi. I know, not a very nice idea for people who really like to stay consistent with their theories, but come on, complex numbers are cool. So dr is what I'm going to use directly, right. Cool. So just this quantity, but then again this is just ds e power I psi of s, and so r is just something like an integral of ds e power I psi of s, right. But remember that, so this times of ds, sure. But remember what psi of s is. Psi of s is just equal to the integration of psi dash of s ds, right. Let's just say like from s naught to some s, I don't know, let's not do that. Yeah, so it's like some function of s plus some constant, like plus some arbitrary constant. This is also a function of s, but the reason I'm doing this constant thing is to show that whatever psi 1 or psi 2 you have in different sort of curves, both of these would be interchangeable up, so both of these would be the same thing up to a constant basically, right. Yeah, so what is this? I mean, yeah, it will be like just that, because the initial psi value, like, it determines everything. This is really hard to show. What do I do? I guess you can do something like this. Let's just say that psi of s is just equal to the integration from s naught to s of psi dash of s ds. So this is just like all the changes added up at the same time plus psi of s naught, right. Yeah. just gonna go use s dash over there because why not, a dummy variable. So that psi of s completely determined by this thing, this psi dash of s thing, which is by the way the kappa thing, right? Yeah. So it's just kappa of s dash ds dash plus this stuff. At the same time, we also have this thing, r is just equal to integration from s naught to s, and this will just be like ds dash. Why did I write it 2 times? It should just be like that, right? So it's just ds dash e power I psi of s dash. But remember, psi of s dash is just this thing, I mean this stuff, completely determined by s dash, so up to a constant. So what we can do is just think of this function as something like, or just let's just think of this function. So from 0 to s of kappa s ds dash dash, let's call that as f of s, right? So this thing will just be like f of s minus f of s naught. Cool. So this whole thing you can just rewrite. You can rewrite this as f of s minus f of s naught, or you know what, actually let's just put that in front, just f of s, and then it's just like e power I psi of s naught minus f of s naught, just some constant, like we don't really care about that. Cool. And so yeah, this is the thing, right? So notice that this is just some sort of constant, you can take it out, so it just becomes e power I psi of s naught minus f of s naught, sure. And then this integral, so just integral of s naught to s ds dash, and then e power I f of s. That's amazing. Cool. Now what I can do is just set s naught to be 0, and you're gonna add some stuff to that. Sure. So just move all of this down. Right, so what I'm going to do is write this as e power I psi of s naught minus f of s naught, integral from 0 to s of ds dash e power s dash over there, e power I f of s dash, and then minus the same stuff, e power I psi of s naught minus f of s naught, all of that, and the integral from 0 to s naught of this stuff. So what that means is you just have some sort of a constant, right? This whole thing is just some plus c, and this whole thing is just some constant. We don't even, I shouldn't say a constant, but just some sort of a rotation, a constant rotation. So this will be just like r, some rotation, and this integral 0 to s ds dash, and this thing e power I, all that stuff, we can rewrite it as, so cosine of f of s dash comma sine of f of s dash, we can do that, and plus some c vector. So this r is a rotation matrix with this angle of rotation, and this is a vector, right? So I should actually be writing a transpose, because what that will is make it a column vector, and that's cool. That's the thing we want. So that's your r vector, right? Complex numbers are really nice, aren't they? But yeah, what this proves is your kappa completely determines everything, because f is completely determined by kappa, and then in turn this stuff is completely determined by f. So whatever this integral is, it's something, and you just rotate that, add some constant vector, and there you go, that's your r vector. Okay, that's amazing. Next thing, so we have to show that any rectangular plane curve whose curvature is a constant is a positive constant, in fact, is a part of a circle. Cool. This shouldn't be hard. So your kappa is 1. So once again, what's kappa? It's just, you know what, never mind. So I'm just gonna do this thing. So dr vector is just equal to like ds e power I psi, right? Yeah, psi of s. So we're just gonna do the usual thing. I mean, it's up to like translation and rotation in any case, right? So we can just find this f vector. So f of s is just the integration of psi dash of s, so basically kappa of s ds right? So just from 0 to s, I'm just going to put a dash over there. So what you can in fact do is just write this as psi of s directly, right? Yeah, I mean, I would usually write f of s, but we can just directly do this stuff. That's a okay parameterization to do, right? Let's just say that at 0, at s equal to 0, your psi is 0 without loss of any generality. So that was really bad. I shouldn't be using accent like that. But anyway, so psi of s is this stuff, and kappa is 1. So this just becomes this. So your psi of s is s. Then what? So your psi of s is s. Wait, what? That doesn't even make sense. How the hell does that even make sense? No, this shouldn't be happening. Something is really wrong with this. What the hell? Your angle is like okay. Actually, this is okay. It isn't that bad, in fact. Because seriously, your angle is just increasing like that, so it's okay. Because yeah, I mean, this is actually fine. Because just think about it. You have a circle. Your s thing is like linearly related to this angle, but then so initially with the x-axis you're making like some angle, and then yeah, that's also just linearly increasing because it's always like perpendicular to this vector whose angle is increasing. So it's completely fine. So you got psi of s. Now what? Now I just want dr vector. Dr vector is it's just dr, I should say just ds e power I psi of s, which is ds and then e power I s, right? And then you just integrate this thing, e power I s ds from s equal to, or I'll just say s dash, from s dash equal to 0 till some s. So let's just call that as r of s. Remember, it's up to like some rotational translation, so we don't really care about that. So what happens is like r of s will just be with this guy's integral, which is just add an I and all that. So just minus I, and then you got e power is, integrate that. So just another e power is, or is plus some sort of a constant, which we don't care about at this point. So yeah, that is the thing. Negative I e power is. That's the thing. Now you can rotate this, right? So you can multiply this thing by iota because that's one sort of a rotation. So what that would do is just make this like equivalent to e power is. And guess what that is? That's a circle. Yeah, that was not bad, huh? Okay, next. Next is circular helix is must be unit tension. Okay. Can you find the principal normal at r as the point of the vector? This stuff. Right. So we are finally going to this new thing called curves in 3D, where you are having this concept of torsion. So it's actually very easy. So what we do is you have some 3D curve. Like I just imagine this thing is in 3D, and at some point you are here, right? And so you are moving in this direction, and your normal vector is maybe in this direction. Since the normal vector and your tangent vector are like perpendicular to each other, right? Because you have a unit parameterization. What that means is, or even if they were not, but in any case, the plane in which both of them lie, that forms the local plane of motion, right? Yeah, so the cross product between these two, it will be like some vector. I don't know how to draw this thing, but it's like coming out of the plane. So that is what we are defining as this binomial vector called b vector. So b vector of s is just equal to your tangent vector of s. I shouldn't write this thing. I should write this t cross n. Yeah. So this vector will in fact change with s, right? So how it changes is what gives us the torsion thing. So essentially, dB upon ds, that happens to be in the direction of minus n, So it's minus tau n, where tau is the torsion. Now, how does this happen? Why is this even happening? Just take a derivative of this stuff. So you just got dB by ds is equal to dt by ds cross n plus t cross dn by ds. Now dt by ds is defined to be capital N. Remember, we did that. So what that means is this stuff is gone. It's not going to matter. So it's just this stuff, tau times ds, so dn by ds, right? But what's that? What is dn by ds, firstly? Dn by ds is something which is essentially perpendicular to n. Once again, following the same logic that we did for t, because once again, the magnitude of n is 1, right? Yeah. How do you even prove this stuff? I don't know. I just don't know. Yeah. But yeah, just take my word for it. N is defined to be such that its magnitude is 1. Alright. And I did say like n is defined to be dt by ds. That's not correct. It's defined to be dt upon ds upon the curvature, because like this guy's magnitude is the kappa thing. So this upon the curvature, right? That's how you define a normal vector. Okay, yeah. So we define this guy's magnitude to be 1. The unit normal is what we call it. So then this stuff dn by ds, that will be necessarily perpendicular to n. Not hard to show. Yeah. Then t cross this stuff, right? dn by ds. So dn by ds is never mind that. dn by ds is perpendicular to n, so it's in the plane defined by b and t. Remember, these three vectors, t, n, and b, they span all of real numbers, all of R3, sorry. T and n, they span a plane, the current plane of motion, and then b is perpendicular to that plane of motion. So yeah, I mean, it shouldn't be hard to see what's going on. So just t and b, those span another plane which is like perpendicular to the plane of motion, right? And n is perpendicular to that instead, right? So then if dn by ds is perpendicular to n, it must lie in that plane, and then you are taking a cross product of that with t. So any component along t, we are disregarding in any case. So what that means is that you're doing something like t cross something, and you just got b hat, right? Or just b for the sake of it. I mean, it's supposed to be unit vector in any case. So something and then b. But that something is basically our tau, because notice that b was defined to be t cross n. So then t cross n, like that's, how do I show this? This is like t, and this thing is n, right? Like this is really bad. I don't know, but imagine this is our x, y, z axis or something like that. But yeah, so if this thing is t, this thing is n, then cross it, you just get b over here. So you are doing something like t cross b. So this stuff, it's like it's gonna give us negative n, right? So this is just happening to be tau times of negative n. So that's why dB by ds is just minus tau n. So yeah, right. So with this formula, we can actually find tau easily. We can just say that tau is negative dB by ds, that times of, so it's that dot product with n, right? Yeah, because remember n is a unit vector, so that's why. Wow, that was something. So you got this formula, but this is not the formula. We can actually manipulate this a lot and make stuff much better. So first thing that we can do is, well, rewrite this dB by ds stuff. Yeah. Right. So b of s is just this stuff. Dt by ds is like perpendicular. So this would be collinear to n. So we are disregarding it. It's just like t cross dn by ds. So this will just be like minus t cross dn by ds, and yeah, and then this dotted with n. So now what we can do is we can use these things. First, t is just r dot, all right, cross dn by ds. So what's that actually? Good question. So n is firstly just r double dot, but what is dn by ds? Dn by ds, huh? N is just this thing. N is just 1 upon kappa dt by ds, right? So then dn by ds would just be negative 1 upon kappa square d kappa by ds, right? And then dt by ds, sorry, not tau, tau is already used specifically. So dt by ds plus 1 upon kappa, this is really bad, get out like this. It's 1 upon kappa d square t by ds squared. Now the thing is, you are taking a cross product with t. Yes. This is actually very weird. And then a dot product with this stuff, right? R double dot. Hey, so for now, let's just let it be. Let it be dn by ds. What we can do is, like, we can rewrite this as a triple product. We can rewrite it as minus the box product of r dot dn by ds and r double dot. Now we can rewrite this, right? So we can circle and we can just say this is going to be like minus dn by ds r double dot r dot, right? That doesn't change anything. So now you can just take, so you can write dn by ds as this stuff. Now r double dot, that's like t dot, right? Since r dot is t, so it's just like the first derivative of the tangent vector. So this term, it won't really matter because it's collinear to this stuff, and you're taking a cross product, so that's going to cancel out. So we'll just have something like 1 upon kappa this thing, so negative, by the way, and you just got dt by ds squared, all that. So you just got dt by ds is what? It's just, well, that's r double dot, isn't it? Wait, that doesn't make sense. Sorry, it's d squared d by, okay, so that's r triple dot, in fact. R triple dot, then you got r double dot and r dot. Yep. So that is the formula, it seems. Is that the formula? Oh, so they have done a lot of other stuff which I don't know what's going on. Oh, so they have defined this a is equal to dv, so it's just the acceleration. So the acceleration is the tangential component plus the normal component, and they are rewriting the torsion as negative db by ds times n. What is b? I guess that's just this capital B thing. It's just b dot, right? Maybe. Well, db by ds, that's okay, that's just b dot, isn't it? Sure. So right, so that's just the rate at which, fine, it's just minus b dot, so b dot dot n, negative dv by ds dot n, right? That's what the torsion is. Just curvature stuff, we are not really interested in that. So this is velocity times the a thing. So velocity would just be tau, so tau cross a. What? Why that particular thing? Why is it cross a? Think. So these first things I got, okay. And what about the minus? Why is it a square? This is in the formula that I am getting. Where did they change something, huh? Yeah, okay, so they flipped it. They flipped r triple dot with r dot, and that dissolved the negative sign. What about the kappa? So the kappa is just magnitude of dt by ds, which is, you know, just the magnitude of r double dot, right? Yeah, so that would just be the acceleration. So why are we taking a cross product? That doesn't matter. makes sense, does it? That's 1 by kappa. Oof, what is going on? Kappa is just a function of what the hell, man? dt by ds, d kappa by ds, some sort of a number. Yeah, I mean this looks okay so far. Why have that? So the acceleration is dv by dt. Is this stuff, right? What is even going on? How did I write dv by ds? That's the thing. Now this isn't correct. This formula isn't what I'm getting. Okay, sure, it's t cross n dot. Wait, what? N dot, So that's tn cross. That makes sense. So t is just r dot, and then this stuff, and then r double dot, because that's just oh yeah, obviously. So r double dot is not what we are supposed to go for, right? We are supposed to go for capital N, not this. Yep. So what is in fact capital N? It's just this thing, right? It's just r double dot, because obviously that, upon kappa. So there's kappa squared actually. That's weird. Kappa squared, Hey, wait a second. Kappa squared. Damn it, what's even going on? So I was saying something like the magnitude of d. Yeah, I mean it's just the magnitude of dt by ds. What's the big deal? So dt by ds is. So we are saying this is going to be not just that, but rather v cross a. Why so? V is just the t thing, and a is. So you don't want kappa apparently. So kappa squared is like something like n squared, So n squared is just, what's n firstly? N is, okay, that would be circular, but okay. So n, what is n? N squared is 1, isn't it? Shit. Okay, kappa you can't just define like that. Sorry. N would be 1. Yeah. Okay. So what's t by ds? The square of that, right? That's what we're looking for. Okay. dt by ds is just hey, something is really messed up about all of this. I can't figure out what. Is this not just the acceleration? It's not apparently, right? No, it's not. It's kappa. It's cross product to. Oh, so you're cutting off the component which is in A. A is. Sure. That kind of makes sense. So velocity v would just be. It'll just be a unit vector. So unit vector cross A. So the magnitude is A, and whatever is the direction of A, you're cutting off the stuff in that. What is the direction of A really? We don't know. We have no idea. Why are you taking a V cross A though? V is in that direction. A is in that direction. So why take a cross product? This is confusing. Did I do something wrong over there? It's supposed to be kappa squared, right? Okay, let's rewrite the whole thing. It's supposed to be dn by ds. Actually, no, let's just write it like this. So this is just t and then dn by ds and n. That's the triple product we are looking for. Now t is just r dot, undoubtedly. dn by ds, so n is just equal to yeah, it would just be like dt by ds, the normalized part of that, just 1 upon kappa dt by ds, that is the thing. Sure, dt by ds is just the acceleration. The yeah, it's a vector, so just r double dot essentially. Is that right? That's what n is, right? I mean, that's how we define n in the first place. But n is just essentially dt by ds, but the normalized part. So that isn't a problem. So this would just be r double dot and 1 by kappa. R double dot upon the magnitude of r double dot. That's the thing. Okay, cool. Unless you have some weird thing going on. I don't know. I don't know what's going on, which it doesn't make sense somehow, does it? So, okay, I think they're going for a non-unit parameterization, which is making them do all of that. So, if I had to do the same thing without using the s thing, what would happen? In that case, your t would just be something like, well, actually let it be just t, and you got dt by ds, which is like dt by dt, and then that upon ds by dt is just a v basically. Sure. Yeah, I guess that's okay. And then you got n over there. So n was defined to be dt by dt upon velocity, right? No, okay, that was n. This stuff is the derivative of that, so it's just okay. That is messed up. So it's dn by dt, that upon ds by dt, which is the velocity. Sure. Now n is defined to be this stuff. So what do? We just do derivative of that. So just minus 1 upon v square dv by dt. So that's messed up. Okay, d capital T by d small t plus 1 by v d square t by, okay, cool. So dt by dt. Oh, this stuff is a scalar, and this thing is collinear with n. So what that means is like we can just kind of forget about this stuff. So this is dn by ds dt, by the way. Yeah, sure. So we can just forget about this stuff completely, and so it just becomes 1 by v d square t upon dt, comma, what the heck, why is this going on? This doesn't even make sense, does it? n, but here you got v cross a. That is not what we're going for, is it? Why do you have v cross a? This doesn't even make sense. Why v cross a? You're not doing any sort of projection or anything. This is just so messed up. Okay, n is just dt by dt, and this thing is just t. That's the thing. Okay, now what is t? T is dr by dt upon, well, the magnitude of that, right? It's just 1 upon the velocity. This is so messed up. This isn't supposed to be v, it's supposed to be, in fact over here as well, it's not supposed to be v, it's supposed to be the magnitude of that. So just dt by dt, right? This as well, it's supposed to be, okay, that's cool. Now what now? Oh, come on, seriously. That's still better. Okay, I'm just frustrated by this now. Right, so what was I doing? Yeah, so t is a unit vector in that direction, and you got this stuff, and then you got that stuff. You can rewrite the whole thing, can't you? Yeah, so you can write t as 1 upon magnitude of v, and that times of v itself, so just 1 upon v r dot, right? Then notice that your d by dt thing just becomes negative 1 upon v dv by t r dot plus, just 1 by v r double dot. Now notice that this stuff is collinear with this capital D in the first place, so we won't actually take that, so it just becomes that. Right, so you can rewrite this whole thing as 1 upon v r dot, and this would just be plus 1 by v r double dot. Right, that's better. Similarly over here as well, firstly just actually take that out, so it just becomes 1 upon the magnitude of dt upon dt, sure, and this is just 1 upon v r dot, 1 upon v r double dot. Now this thing I'm pretty sure it's just going to be like 1 upon v r triple dot, yes, obviously it's going to be that, right? Well, we never know. So actually take the derivative of this thing, right? So yeah, right, you better take the derivative first. So it just happens to be negative 1 upon v square dv by dt r dot plus 1 upon v r double dot. Well, the derivative of that would just be like what? It's just negative 2, so that negative is cancelled, so just 2 upon v cubed dv by dt squared r dot, this guy's derivative, which is like negative 1 upon v squared dv by dt, so d squared by dt, okay, right, that stuff, and then r dot, sure, and then plus this stuff, so just negative 1 upon v square dv by dt r double dot. So this is covered by that, this is covered by that, this is covered by that, right? All of this is like perpendicular, so none of this like really matters. Plus 1 upon v r triple dot. Yeah, that's the way it is. So we just have 1 upon v r triple dot over there. So it turns out that this thing is something like 1 upon, that's a square by the way, it's just 1 upon d by dt squared, and then it's got v cubed. Sure. Now how does that become v cross a squared? I have no clue. How does that even happen? You got a v cube, huh? Cross product. What? Why? Something isn't quite right. I don't know what the problem is. It was just t dn by ds and n. Shouldn't be such a big deal. N is certainly that. Yeah, n is certainly that. No big deal. The t thing is also correct. Your dn by ds is actually messed up because it's not just this. If n is this, or at least the component perpendicular is this, right. Okay, I see what the problem is. So the way we defined it, your n was this thing, 1 upon magnitude of dt by dt, and then what? And then dt by dt itself, right? So your dn by ds, which would be something like this stuff, that would be, well, we take the derivative of this thing, so just negative 1 upon squared. Wow, this is really not good. And then the inside square, sure, so just that's good. So okay, what even is that thing actually? This is really not very good. What the so it doesn't matter actually, it doesn't really matter. This d by dt of this stuff, and you got dt by dt. The thing is, it doesn't matter because this thing is it's perpendicular to this thing, so you can just kind of ignore that, and so it just becomes something like the part which actually matters is something like 1 upon dt by dt, the derivative of that, so just d squared e by dt squared, sure. but that times obviously ds by dt. So ds by dt is just v. So what do you really have? You just have this thing, t, this stuff, just v by dt, d square d by dt square, comma 1 upon dt by dt. Right. Okay. So now you can do this. You can write this as v upon squared, right? And then t d square d by dt square and dt by dt. Now this is doable, because now you can just take the v cube, and so this just becomes exactly just that. So there was a negative, by the way. So this just becomes exactly just 1 upon the magnitude of dt by dt squared v squared, sure, and that times this determinant. So the box product is just r dot, so r dot r double dot and then r triple dot. Yeah, so that's okay. Now what we have to show is that this quantity is the same as this quantity, v cross a squared. So okay, shut off. So okay, dt by dt squared and then v squared. Yeah. So both of these are actually going in the same direction, isn't that right? Yeah, they are. No, wait. Okay, this thing is not going in that direction, isn't it? So dt by dt. Yeah. So what is that? This thing is just d by dt of 1 upon v r dot. Yeah. Which is what? Which is just negative 1 upon v squared. Okay, this is actually very weird, isn't it? There's a component which is going in that. This is a cool. I think this is where the acceleration formula comes in, doesn't it? Yeah, it does. Sure. So it's just dr by dt. So dv by dt. Sorry. Then you got r dot plus 1 upon v r double dot. Interesting. And this whole thing times v squared. So it just becomes something like negative dv by dt r dot plus this v r double dot. Interesting. And so what we are claiming is that this is the same thing as the magnitude of, so or that this guy's magnitude is the same thing as that. Sure. Right. So basically it's the magnitude of v r double dot minus dv by dt r dot. Yeah. So how is that v cross a? dv by dt. What is acceleration? What is dv by dt? Yeah, it will just be that. Hey, so I think we kind of did the acceleration at some point, right? Yes, we did it, in fact. So acceleration, which is dv by, oh okay, this v is by the way different from the other v, so just keep that in mind. So it's this thing. It's so yeah, this is clearly the tangential component and this is the normal component, right? Okay. So r double dot is the acceleration. Oh, okay. This is not not like that. Wow. So what you know is that r double dot is written as, so it's d square s by dt square or whatever. So just well, what's ds by dt is just v. So just dv by dt and this t vector, which is something like 1 upon v times of dr by dt, so just r dot, okay, plus this, what is this, kappa? Well, that's ds by dt, oh, that's v, so that's v dt by ds, okay, and you got n over there. cs by dt, oh, this is messed up, isn't it? Sure, that's normal vector, isn't it? I'm just gonna write it like that, so just v times of this stuff, so ds by dt is just v once again, so this just happens to be v cube, it seems. Wait, oh, that thing is supposed to be kappa, okay, that is in fact kappa, so just kappa v squared and then n, right? That's the way it is. If you use that, then it just becomes like, okay, v r double dot, that's just something like kappa v cube n, then this stuff. Yeah, so that just cancels. Yeah, that just cancels. So the remaining part is what we care about. Just it's just kappa v cube apparently. Sure, there's a v over there. What is kappa really? Are we even sure I'm making some sort of a correct thing? This looks weird. Just kappa v cube. What? Well, dt by dt, that's a v squared. That's like ds by dt, right? That's a square over there. What the hell? I don't know. Something isn't going right. Just I can't sense what's not going right. It's a v cube, isn't it? It's supposed to have a v over there. Wow, I'm really not in the mood to be doing all of this. It's v squared over there, right? It has to be v squared. What else can it be? This is bad. It's v square, so v square times of that, it is this quantity, which happens to be kappa v cube. Why? And how is that v cross a? This is a. This, let's put that over there. This is va minus all of that, huh? Hey, oh, okay, I see. Wait, no, I still don't see. This kappa v squared n, that is like dealing with that stuff. But the magnitude of this is kappa v squared. Sure. Okay, v cube, but the point is just that. So kappa v cube is not the same thing as this, is it? Well, this wasn't too hard to figure out. Okay, I don't know. I'm gonna see into that later on. But yeah, this is not the formula I'm getting. I'm getting a very different formula. Anyway, so got some examples, and we got a theorem which says that unit speed curves in R's with the same curvature and the same torsion. Then there is a rigid motion m such that so for torsion as well, we just have translation plus rotation thing giving the same thing. Okay, do I really need to prove that at this point? Because yeah, I mean, if it's unit speed and your normal vectors derivative, that thing is defined, so you know how to move, and once you know how to move, yeah, everything is fixed at that point. So it's a unit speed. At the same time, you also have a unit curvature. not unit curvature actually, it's just the same curvature, right? Same torsion as well for all S. Sure. Yeah, I agree. There is a rigid motion like that. So the proof is let R be a regular curve in R3 with nowhere vanishing curvature. That means tau is defined, and the image of R is contained in a plane if and only if tau is 0 at every point of the curve. Okay. So this is a proposition that we are proving first, and so this is not proved. This thing is not proved, but this proposition is like being proved. So the proposition is that let tau be a regular curve in R cube with nowhere vanishing curvature. That means that tau is defined. Okay, cool. Wait, do you need the curvature to define tau? Yeah, I mean you have to define n, and that way you have to, sure, you need a curvature. Then the image of R is contained in a plane if tau is 0 at every point of, so yeah, sure, if tau is 0, then your normal vector never changes, and if it never changes, that means your plane of motion never changes, and if your plane of motion is never changing, that means you are moving in a plane throughout, right? So then tau is 0. This is actually very trivial, like the forward is pretty trivial, that if your tau is not changing, you are moving in a plane, right? And if you are moving in a plane, obviously your tau is not, obviously your b is not changing, so that means your tau is 0. So this was pretty easy. Yeah, so curve lies in a plane, then obviously your b vector is like always going to be perpendicular to that, right? And the converse is that suppose tau is 0, well, yeah, so to find a and d scalar such that what are they even writing over there? Oh, okay, such that R dot A vector. So you want to find a plane such that it's always going to be on there. So you have tau equal to 0, that implies b dot equal to 0, which means b is a constant, so that just means, sure, okay, so b dot R is a constant, so b is a constant vector. Okay, what is this stuff? Is this gamma or what? I'm just going to use it as a R thing. So R dot B is constant. Why? What product would be? Isn't R dot B? Wait, okay, so the R dot B is in fact constant. Oh, okay, that actually makes sense. R dot B would in fact be constant, right? B is a constant, so R dot B is also a constant. Oh, so we want to show that it's also constant. Right. So just consider this function R dot B as a function of R. Take its derivative, just got R dot B plus B dot R. B dot R is 0 because B dot is 0. So that just becomes R dot B. But what is B? B is defined to be T cross N. But then T is collinear with R dot. So this dot product is also 0. Yeah. So then R is contained in the plane because R dot B is constant everywhere. Yes, okay, that was doable. Right. Okay, so that does the proposition. The theorem, I'm not sure I have enough energy to be proving this theorem, and I also don't know if I'm gonna be proving this thing. It looks weird, like I can't prove it directly somehow, but yeah, I'll see what I can do. So I'll see you guys in the next video.